Hello. So today we're going to keep talking about performance, and we're going to sort of, on Friday, when we started talking about performance, we had sort of gotten into the muck. And today we'll try to get out of the muck and talk a little bit more about what actually to do. Don't have anything to say. Do assignment 3. How many people have started assignment 3? All right, this is good. How many people have finished assignment 3? I know. We were done like a month ago. All right. So you have a couple weeks left, and as the deadline gets closer, we will add some office hours as we did last time. But please, work on the assignment. It's a cool assignment. It'll, you guys will get a big kick out of it when you get it working. Okay. Any questions about what we talked about on Friday? Friday was a long time ago. Distant past. All right. So, what were some of the, what were some of the challenges to improving system performance that we talked about on Friday? Who remembers one of them? One of the things we discussed, Tasha.
The tools you use to measure can change how your system performs.
Yeah. So measurement can be an intrusive process, right? So when I take a measurement, I might affect the system, and that can have two problems, right? One problem is when I look at the data, I have to make sure to factor out the impact of whatever tool I'm using to do the measurement. The second problem is that measurement might make whatever problem I'm trying to find go away. So those are two separate issues, right? What else? Yeah, Doug.
What are you measuring in the first place?
Yeah, trying to make sure that we're measuring the right thing, right? What are we trying to measure, and does that thing that we're measuring actually have an impact on the system in the way that we care about it, right? Are we measuring the right thing? What else? There were some more fundamental problems. Guys remember? So we're talking mostly about measurement here. That's what we talked about on Friday. But what else was hard to measure? You guys are all sort of assuming that you can measure something. That there's a particular measurement that you can actually use on a system that might not be so easy to use. What is that? What is performance always sort of relative to? Yeah.
Some of the measurements are too small to real measurement.
Right, too small in terms of what?
Okay.
Time, right? How do you measure time on these systems, especially for operations that are really, really fast, right? So today we're going to talk more about these last two sections, right? So we talked a lot about measurement. We'll review that briefly, right? And we'll talk today about sort of some of the pitfalls involved in examining the results, right? Let's say that we can do these measurements, right? How do we analyze the results, and then what do we do about it, right? We talked a little bit about the difference between models and simulations. What were the distinguishing characteristics of a model, right? If I gave you a model of system performance, how would you know it was a model as opposed to a simulation? Yeah.
Not real. It's like a bunch of mathematical formulations.
Yeah, it's like a model is a set of formulas, and because of that, I could potentially can come to strong conclusions or make strong guarantees about how the system works. The problem is that those models usually obscure a lot of important details, right? What about a simulator? What is the goal of using a simulator? Why would I write a simulator? Yeah.
A simulator tries to simulate the hardware that you're working with.
Right. But what's the advantages of doing that as opposed to using real hardware? Yeah.
Test on a wide variety of stuff as well as have the simulation keep benchmarks and keep statistics and stuff.
Yeah. So the simulator, there's two things that came out of that. So right, one is something actually we didn't talk about, but the simulator might give me access to hardware or to types of hardware that I don't actually have, right? Maybe that hardware doesn't exist, right? Or maybe I just don't have a copy of it, right? So if I had a really good, hard drive simulator, I could test my file system on a lot of different types of underlying storage devices and be able to say something about its performance, even without having a copy of all of those. What else is nice about simulators as opposed to real devices? They also might have inbuilt measurement. They might allow me to measure things that would be difficult to measure on the actual device. I might be able to collect statistics about hard drive performance, for example, that the hard drive themselves won't tell me, right? Because either they just don't expose this information, right? But what else do I usually like about simulations when compared with real systems? Yeah.
They're very flexible.
They are very flexible. It's almost going into, yeah. So I can potentially change a lot of different parameters. But what else do they do? It's almost in the opposite direction of flexibility. What do they generally, what are they that real systems are generally not? They're repeatable, right? I take the same, I mean, how many people have ever used a simulator? How many people have used one in this class? All your hands should be up, right? I mean, you're running a simulator, right? Sys161 is a architectural simulator. And if you've noticed sometimes, if you just give it the exact right series of inputs, you can actually get it to exhibit repeatable behavior, right? Particularly by setting the same random seed and you know. Now, of course, once you start interacting with the system, who knows? All bets are off, and some of your interaction starts to produce noise that's going to cause it to go down a different path, right? But yeah, Sys161 is a simulator, and I don't know if we give you guys the code for it or not. We probably do. You're looking, you know. This is a pretty simple architecture, so you could write your own little version of that. The nice thing about simulations is that the speed up that you can achieve. Now, the other some simulators, this is interesting, right? Some simulators are faster to run than the device or the hardware of the system that they're simulating because they're excluding a lot of details. On the other hand, there are also simulators that are much slower than the device that they're running, right? Like a full architectural simulator. I mean, Sys161 is actually a lot slower than a real piece of hardware would be. The nice thing is it doesn't matter for your system because it's so simple, right? But if you actually had a piece of bare metal that you could run your OS161 kernel on, which would be pretty cool, actually, it would definitely outperform the little simulator we have, right? And in the worst case, if you have problems with your simulator, that can pollute all your results, right? We talked about, problems just choosing things to compare, right? There's a lot of different ways to line up different parts of the system to try to determine which one is better. We talked about benchmarking, right? It's a little longer review than usual because this was on Friday, right? Which of course, it's a whole weekend between us. And we talked about different types of benchmarks, different programs that I might use, that I might run on the system to generate measurements that I can use to try to compare different approaches, or in the case that we're going to talk about, find and improve the performance of part of the system, right? All right, let's get through this, right? So we talked about different types of benchmarks I want to use, for example, for the VM system, right? And the problems with benchmarks, okay. And the problems with benchmarks, and the problems with benchmarks, all right. So, and this is something to keep in mind for today, right? Part of what we wanted to accomplish when we use benchmarks is have an objective, right? What am I trying to do? What specific part of the system is the problem, and is making that part faster going to help? And today we'll introduce you to some performance, some math underlying performance that allows you to determine how effective this is going to be, right? Okay. Any questions about this before we go on? Benchmarks, measurement, etc. All right. So what we've done so far is, we figured out potentially what to measure, how to measure the system, which tool to use, right? So we're, and really what we're talking about today applies mainly to simulations and real systems, right? Models have their own problems that we're not really going to discuss, right? We've chosen what to run, right? We have our benchmark, we've run it, it's producing a set of output, right? So now we have some measurements that are produced by the benchmark, and we're assuming that those measurements are of a system that's behaving the way that we think it will and doing something that approximates what we actually want it to do, right? And again, those are big ifs, but let's just pretend that we got this far, right? So now what do we do, right? I have a set of measurements. Now we get to the interesting part, right? This is all kind of fun, right? But now this is when the real sort of brainstorming begins, right? Because I have a set of results, I have to look at them. And then when I'm improving performance, remember I'm in this iterative loop, which is I measure the system, I figure out what's wrong with it, or what just the weakest link is, what I can improve. I do that, and then I have to start over, right? And then we get to the bottom. We'll go, there was a beer in here somewhere, I think, but it's gone now. It's Wednesday, it's not Friday anymore. All right, so how many people feel like they have a real deep grasp of statistics and statistical methods? All right, somebody does. Like a former statistics major, maybe. And again, a lot of us are computer scientists because we like fell off the boat of another discipline that was more math oriented, right? I'm in this category, right? So I'm not poking fun. So this is kind of like our version. I remember someone, I think it was David Patterson, had what he called the computer scientific method, right? There's the scientific method, and then there's the computer scientific method, right? Which is not what you want to be doing. So this is kind of the computer scientific method, right? Okay, I ran it twice. I computed an average. Done, right? I mean, I guess that's the minimum number of runs required to make a meaningful average. And okay, so I'm finished, right? And maybe, this is only really like if I have some extra time at the end of the day, or I'm looking for brownie points, I'll put error bars on the graph, right? Maybe, right? Because error bars, I mean, now if you want error bars, now I have to run like maybe 3 times, right? So this is really increasing my load. You guys should do better. And I have to say, I think this is actually becoming probably increasingly important, even for those of us that want to, that just want to build real systems and do cool stuff in the world, because a lot of the systems you guys will build and develop on are getting bigger, they're getting more complicated, they have more to do with data, right? So, the days of lore where you could just sort of like, build real cool systems with just, some intuition and a slide rule are probably over, right? Like a lot of, building real systems and getting them to work well has to do with understanding data, right? Data about the system or data the system's actually using to do something, right? But at the same time, let's not abandon our intuition already. So what I've told my students, and what I would suggest you guys do whenever you're trying to solve a performance problem, is make a prediction, right? In the scientific method, right? This is called a hypothesis, right? And again, computer scientists don't always do this, but before you generate a graph of your system, apply your intuition to what the graph should look like, right? So I'm going to look at 2 different page replacement algorithms under a certain workload, and which one is going to perform better? And by how much is that one going to perform better, right? If I'm looking at, the performance to swap in and out a certain number of pages, I mean, you can imagine that there's a relationship there that you should be able to sort of visualize. So sometimes it's helpful to just actually draw the graph, right? Get out a piece of paper and just sketch out, here's what the graph is going to look like, right? Here's what my data is going to look like. Or if it's not a graph, just make a prediction. This page replacement algorithm will be faster than this one on this particular workload, and here's why I think so, right? There's 2 reasons to do this, right? One is because it forces you to go through the mental process of thinking about what type of hypothesis you're trying to test. Sometimes when you do that, you realize that, whoops, I'm actually, the benchmark that I'm running isn't actually the right one to evaluate this particular hypothesis, right? So that's the first problem. The second thing it does is it exercises your intuition about how systems behave, right? And I actually do think that part of being a good computer scientist is having some sense of intuition about how the system is going to behave, right? How pieces of code that you built actually work at a high level. This is not something that you're born with, right? It's not a skill that was needed, by our ancestors, 100,000 years ago as they were roaming around Africa hunting things, right? Like this is a learned ability, and part of the way you learn it is you test yourself by making predictions, running experiments, and sort of rebuilding your intuition over time, right? So make a prediction. Just said that. Then after you actually collect real results, you go back, right? So you take the graph you drew, the graph you produced. You put them side by side, you look at them, and if they match, you're done, right? Well, not always, right? If they don't match, then one of 2 things is the problem, right? Either you don't understand how the system worked, right, or is actually working, and that's okay. If you've learned something from the experience, you may be developing your intuition about how these systems work, which is really helpful. Or it's possible that something else is going on, right? That something else could be your simulator is broken, right? There's noise in the measurements that you made. But in general, I would say that neither a match here or lack of one is really a strong data point, especially when you're getting started. I mean, when you've been doing this for 30 years, you may be willing to say, okay, I know that that data is wrong, right? Like, that can't be right, right? I have such a strong intuition about how the system behaves that there is no way that that graph is right. But when you're just starting out, it's more like, I wonder why the data looks different than I thought it did. And again, this is also a nice way to validate simulators, right? If you, particularly if you compare data from a real system to an equivalent simulator, right? The simulator is behaving quite different than the real system does when exposed to the same benchmark and measured in the same way, then there's probably a problem, right? Either with the way you're running the measurements on the real system or with the simulator itself, right? The next thing, once you have some real data, and this is a mistake I think that people are, including people practicing the computer scientific method, are really prone to, right? Which is summary statistics, right? Averages. Let's compute an average, right? Why not? It's easy, I take a bunch of numbers, I add them together, I divide by another number, and now I have this statistic, right? I'm doing statistics, right? This is awesome. I feel like, I don't know, I could probably give a whole lecture about how broken averages are and why you should really rarely use them to describe any sort of data, right? Averages tell you very little about information, right? Particularly information that's not completely normally distributed. In fact, they tell you almost nothing, right? The average income in this country is probably like twice what the median income is, right? The average income sounds awesome until you realize that nobody is making that much money, right? All right, so let's look at the following data from 2 experiments, right? So, and the median is better, but the median's not a panacea either, right? I like medians more than means. They tell you something concrete about the data. What does the average say? I mean, the average is not necessarily a meaningful statistic. The median at least tells me, how the data separates top and bottom, right? So here's 2 data sets. Let's say that you measured your system, and in one case, here was the result of your measurements when you looked at the distribution. And in the second case, here was the result, right? And there have been, I've heard stories from friends who have done these types of measurements and have accidentally fused this type of data into one statistic, right? If you compute a mean and a median, these systems look identical, right? They can look identical. But their behavior is totally different, right? For example, this could be the time it takes to perform some function, right? You're trying to do a profile of your system. You measure this, and in this case, this looks nice, right? This is pretty predictable. This second function looks like it performs identically, but there's actually 2 subcases hidden in here, right? Obviously, the performance of this function is somehow very bivariate, right? Something in one case it's fast, in the other case it's slow. Right? Figuring out which one of those is which might help you move all of this into here, right? Which would be great. So this is, examine the bottom of the slide. So looking at, even if you're going to eventually compute summary statistics for data like this, looking at the raw data is really important, right? It gives you a sense of what things look like and can help you identify cases like this, right? When the outliers, right? So people say, oh, well, there's this one data point I can't explain, right? And must have been, cache effects, right? I must have just, I don't know, something else was running in the background. Once you start trying to explain data away, particularly when you're measuring real systems, there's thousands of excuses you can come up with, right? The NTP time server got off, right? The packet link was congested because somebody was downloading a huge movie file. Like, who knows, right? You can just start making things up. But you should think about trying to, embrace the outliers in your data set and at least try to squeeze everything you can out of them, right? Try to figure out what they actually mean. Don't start explaining them away. try to explain them to yourself. Say, why is this, why is this here, right? They can be. There are cases where there are noise in your data, they're a result of some sort of problem, but there are cases where there's something happening in the data set that you don't understand, right? That they're actually really meaningful, and if you sweep them under the rug, they may come back to bite. Right? All right. So now that we've sort of now that we've decided to actually look at our raw data before we compute summary statistics, now the next question becomes what part of a complex system should you start improving? And this sounds pretty easy, right? I start with the slow part, right? I find the slowest function in my entire system, and I work tirelessly until that function is faster, right? This is guaranteed to produce a massive improvement in performance, right? Why not? Sounds good. Why not? Adam?
Because even the slowest performing part of the system may not be the source of that performance dip.
But why not? Why wouldn't it be? It's the slowest part. Come on. Kevin.
Well, it all depends on what part is being used the most to actually slow it down. If you have a really slow part of your system, but it's only accessed once, then improving that won't cause a very large improvement.
Yeah, so just because something is slow doesn't mean that. So, for example, here's if the slowest, well, I'll get to this in a minute. If the slowest part of the system was a code path that was never executed during my trace, right? Then its contribution to the performance of the system that I measured is what? 0, right? So now I'm not even working on a part of the system that's even being measured, right? Now, and this is sort of a separate problem. The other problem that happens when people decide what part of their system to optimize is a lot of people think that they can skip all of the steps that, because we've been talking about this for like a lecture and a half, right? Measurement, and I got to pick a benchmark, and then I have to analyze the data. No. I've been doing this a long time. I'm pretty good at this. I know the part of the system that's slow. I just know it, right? I know it deep in my heart, right? When I was writing it, there was this one part where it was like late at night, and I was like, man, I'm just going to use some sort of terrible, brute force algorithm here, and I'll come back to this later. Maybe I left a comment in the code being like, this is really terrible, someone should fix it, right? And I knew what I learned about this new algorithms in my algorithms class. I was going to replace it with some sort of red-black tree or something and make it really cool, or maybe a Fibonacci heap, right? Because those are awesome. Yeah, so a lot of times, if you just set somebody loose on improving the performance of a system, they won't even bother with all the stuff they talked about. They'll just go find the part of the code that looks complicated, right? Or the part that's really ugly, right? It looks, oh yeah, God, there's a linear search. Oh no, got to get rid of that, right? Now let's spend several days implementing some sort of hash table because I remember, once I was puzzling my way through part of the Windows source code, and I was trying to follow this code path. It was really long, and I was in the middle of this really complicated VM code, and I decided, because I was trying to look at stuff on single processor, normal machines. But Windows, like other operating systems, has lots of special cases for if the machine has 3 gigabytes of memory and was built in the year 1997, do this as opposed to this other stuff. So just a lot of, because they're trying to support a lot of different types of hardware. So I thought maybe, and there's all these preprocessor macros everywhere, right? Like ifdef, this confusing thing that you've never heard of, right? Huge blob of code. So I thought, I don't know, I was just I'm not sure I'm in the right part of the code. So maybe I'll just run the preprocessor and see what comes out of this file, right? So I ran the preprocessor with the options I'd enabled, and guess what was left in the file? Nothing, right? The whole thing I had spent about 2 hours looking at was just gone, right? I had followed the code path down a dead end, right? So, and it's possible that if you let people loose on improving a part of a system, they'll actually end up working on something that's not even contributing at all, right? The code path that's never used or never run, right? So just don't trust yourselves here, right? You don't know what the problem is, right? I'm sorry, even I don't, right? I wouldn't even trust myself here. I think I have a pretty good intuition about how systems work, but I wouldn't pretend that I have some idea of what the performance problem is, right? So again, we'll get to this slowly. So if I And part of the problem is when you do profiling in certain general cases, right? If I knew this about the system, I already knew going in that I had this one function that took 5 minutes to execute and a section function that took 5 seconds to execute, then again, now I have some data. And so, yeah, I've done all my background work. I'm going to start working on foo. But if foo is never called, right, or if foo is only called once in a while, then it's possible that I'm working on the wrong problem, right? So, and there's two actual problems with this sort of logic. One is, first of all, how significant is foo? That's sort of what we've been focusing on. But another thing that people tend to overlook is how hard is it going to be to squeeze some more performance out of foo, right? Maybe foo is a piece of code that's been hacked on over and over and over by misguided people trying to improve performance, right? And it's already using fancy data structures and, you know, really careful memory allocation and all sorts of things. So it's not clear that you're even going to be able to make a dent, right? So the first thing is figuring out what to, you know, so there's two components, right? One is what's the contribution of this code to the overall performance, and the other is where are you actually likely to make it improve? So let's talk about significance, right? Because that's what we're, at this point, with the data we've collected, we're probably able to measure that, right? We have some idea of what foo is contributing to the overall performance of the system, right? And now, finally, we've all been building up to this. Amdahl, how many people have heard of Amdahl's law before? Okay, good, right? So, you know, essentially what Amdahl's law says is that any effort to improve performance is constrained by the parts of the system that you're not working on, right? So if the part of the system I'm working on contributes 5% to the overall performance of the system, what's the maximum speed up I can achieve? 5%, right? Probably not, and that's an upper bound, right? Because that's if somehow I made it go away, right? Which is an awesome way to improve performance, right? Is start removing features. But that's not usually what you end up doing, right? You usually try to preserve what the code did. So, and again, so now imagine even that I have some idea of how difficult it's going to be or how much performance improvement there is. And let's say I'm going to keep trying to tempt you guys with these false choices, right? So now let's say you have the choice of, you have some sort of pre-vision. You can see the future. And you know that you can improve the performance of foo from 5 minutes to 1 minute, right? Alternatively, in the same amount of time, you can improve the performance of bar from 5 seconds to 4 seconds, right? So now it's clear, right? No, it's not clear, right? Yeah, but it's again, this is the problem, right? Like a lot of your intuition leads you in the wrong direction. This seems pretty obvious. I'm going to say 4 minutes, right? Come on. And I've reduced foo by 80%. I mean, wow, you know? I mean, you're going to get a great sense of satisfaction when you complete your improvements to foo, right? That reduce it, you know, that reduce its runtime by 80%, right? Like that'll get you a big pat on your own back. From yourself, basically, from anyone else. So again, if our program spends 95% of its time running bar, right, and only 0.1% running foo, then the speed up from improving foo, 1/4 second. Speed up from improving bar, 1 second, right? I can't remember what this was over, like 10 seconds or something like that, right? So here you go, right? So what's an example of, I mean, maybe this is seeming far-fetched, right? But can people think of examples of foo and bar, particularly from operating systems that we've been talking about? Well, okay, you have to say both, it has to be both foo and bar, right? So what part of the, okay, so page fault would be what? Page fault is to bar as what is to foo? Let's find something that it's in the same subsystem, though. Yeah, it could be. Yeah. Ooh, no, I think that would be the other way around, right? TLB fault is to bar as page fault is to foo. Let's just talk about, why don't we just talk about some bars for a minute, right? What are some of the bars in the kernel? code paths that get executed all the time. Yeah. Context switching, right? That's a hot path. I mean, if you work, for example, in performance for a server, I think I've said this before, if you went to Microsoft and you were on the server performance team, and on your first day at work, you went into your boss's office and you were like, you know what? I think I found an unnecessary instruction in the context switch code, right? He would be like, okay, you're promoted. Immediately, because you're going to improve performance by like a pretty large percentage, because there's not that many instructions on that code path. It's already, people have been poring over it for years already, and it gets executed thousands of times a second, right? So context switching, what else? People came up with some of these page faults, right? TLB faults in particular, right? On software managed TLBs. On hardware managed TLBs, you don't have to worry about that. But page faults still, I mean, that's definitely more of a bar than a foo, right? What about some foos? What's that? Yeah, boot, potentially, right? Who cares how long boot takes? Well, people do care, right? But it usually takes it like a reasonable amount of time, right? What else? That's something that only runs once in a while, yeah.
Create for certain things.
Creating objects? Yeah, maybe. Maybe if that object's going to live for a long time and I'm going to use it for a while, yeah.
Certain maintenance activities?
Yeah, like page cleaning, right? Stuff like that. So anyway, I mean, it's just a little thought experiment. And I just said that, right? Yeah, like literally, not only would you get a promotion, right, but your entire team would get like a month off. Right? You would go to Tahiti with the right. So I think it's important to sort of like deal with some of the implications of Amdahl's law, right? And one of the things that Amdahl's law is designed to help you do is ignore the thing that you think is the worst, right? Ignore your intuition here, right? Ignore what you think the problem is, right? And measure something, right? Measure the system, measure what the problem is, right? And then fix the thing that's killing you, right? Don't fix the ugly thing, right? If the ugly thing only runs once a day, right? Fix the thing that's doing damage, right? And this is one of my favorite, I hadn't thought about this till I started teaching in this class, but one of the things I think that's fascinating about Amdahl's law is also the following, right? So the more time this is sort of my second corollary to Amdahl's law. The more time you spend working on one part of the system, the more what? The less likely you are that you're still working on the right problem, right? Because you found, you started at the top, you found the thing that was the problem, you worked on it, and now the problem is something else is killing you, right? So the longer you work on one part of the system, now if that part of the system is like 95% of the performance problem, then okay, you can work on it for a while, right? But that's usually not the case, right? Usually the case is that your performance is the result of a bunch of different things that are making similar contributions. So once you've made some improvements in one area, it's time to stop and start over, right? So that you figure out, okay, am I still working on the top order bit? So for the rest of class, I want to go through, I want to talk a little bit about what to do, right? So now we know how to figure out how to measure things, what to run, how to analyze your data, how to find the part that needs to be fixed or improved. But now what do you do, right? And this, look, like, there's no silver bullet here, right? I mean, every piece of code is different. Every system is different, but there have been, so this is interesting, right? Because this paper was written in 1983, right? When I was 4, and most of you guys weren't born yet, right? But even then, right, people in the systems community were already sort of collecting these kernels of wisdom, right? And this is a very seminal paper, right? There's no way you could write this paper today, right? It's like everyone knows this, right? Because Butler Lampson wrote it, in 1983. So we'll put, and this paper, which you guys, I'll put up a link to it on Piazza, and you guys should look at it. It's a little, I have to say, the structure of it, he structures it after the advice that Polonius gives to his son in, which Shakespeare is that? I can't remember. Anyway, Someone should know this. You guys are educated young people. You don't, what's that?
Was it Hamlet?
Hamlet? Yeah, it is. Yeah, in Hamlet, right? So there's this whole monologue that one of the characters goes on in Hamlet with all this advice. Neither a borrower nor a lender be. You guys may have heard that one. That's from that. And I don't know. I think it's a little bit of a funny way to structure a paper about a performance improvement. But anyway, it's his paper, so he can do it however he wants. So we'll talk about a couple of them, and we'll put them in the context of virtual memory performance. But there's a bunch of hints in this paper, and they're not just about performance, right? He also talks about functionality and fault tolerance, right? So how do you make things fast? How do you make them safe? And how do you get them to work, right? And how do you choose what to build and good interface design, right? So there's a lot of nice hints about interface design in this paper as well. It's a very, very interesting paper, and it's very worth reading, right? Cache answers, right? So, you know, in general, once you've done something, if that thing is expensive to do, don't do it again. Keep the answer around. There's actually a whole interesting effort going on in the programming languages community called memoization, right? So someone was telling me about a system recently where they can actually detect that the system has returned to an identical state, and then rather than running the computation that they've already done forward, they just return whatever result they got before, right? So essentially, you know, you can imagine if a function is deterministic in its inputs, and I see the function being called again with the same inputs, I don't run it again. Just return the same result as last time, right? Pretty simple. Except I think it's probably hard to get to work. So what about caching answers? How can we use this in operating system TOB management? What's the way to apply this idea of caching answers? We talked about this before. So what could you consider to be answers here? What's the work that we do that's preserved in the TLB? At any given moment in time, the TLB is stored. I mean, what does the TLB store? Yeah.
Translation from virtual to physical address.
Yeah, address translations. And every one of those address translations required a fault, right? That your carefully crafted VM fault code had to handle, right? You had to do all this work. You had to look things up, you know, figure out where the page was. And so there's all this work that was done in order to do one thing, right? Which was to simply load a translation into the TLB. So the system that we've given you for assignment 3, when are those, what's one problem that you could foresee with, I've done all this work, I have an answer in the TLB. When do you lose those answers right now? Yeah. Yeah, so on a context switch, the safe thing to do, right, is just flush the TLB, right? Clearly the translations aren't relevant for the next process because all of my virtual to physical address translations are always done in a process context, so I just flush the TLB, right? How could I apply the cache answers approach here to TLB management? What do I do instead of flushing the TLB? Yeah, just save the entries that were in the TLB when there's a context switch, and the next time the process starts running, restore them. I did all this work to produce these answers. Why repeat it? You can repeat it and it'll work, but I already have these values, right? Put them back where you found them, right? You guys are welcome to try this for assignment 3. Don't do it when you're getting started. Do it later, right? Get other things to work first, but there's no reason that this shouldn't work, right? It's quite straightforward, all right? Use hints, right? So hints are information about the system that is not, they're not required for correctness, right? That's why they're called hints. But they can improve performance, right? The idea with the hint is that nothing on the system should fail if the hint is wrong. But if the hint is right, I might have a chance to improve performance, right? So what's an example of a place already in the kernel where I use hints to try to improve performance in the VM system? That's an example of a hint that the VM system uses to improve performance. Something that, again, that's not required for correctness, but if it's right, will improve performance. Yeah, Doug.
Swapping algorithm?
Yeah, so what's the hint?
The hint is don't randomly throw out a page, use a page that is less likely to be used again soon.
Yeah, so remember my page replacement algorithms already use hints, right? I mean, we've usually talked about this in the context of doing what? Using the past to predict the future, but the past is only a source of hints, right? The past is not a source of truth. Well, I guess, I don't know, that's probably a deep philosophical statement that I should make sure to limit only to page replacement algorithms, right? But the past is a source of hints about what might happen in the future, right? So if the hints are right, then a page that hasn't been touched for a while isn't going to be touched for another long while, right? What happens if the hints are wrong? Do they affect correctness? No, because if I put the wrong page on disk, I can still go get it immediately once you fall upon it right after I fall upon it, right? So in the case where my hints are wrong, I'm okay. If the hints are right, I do well, right? All right, what about, so compute in the background, right? Move computation off of the sort of what you could think of as the eyeball path, right? Don't do something while the user is waiting. Prepare while the user is not sort of bottlenecked by that part of the system, right? So that you're ready. So what's an example of something that the virtual memory system does in the background to try to improve performance? There's a couple of these, actually. What's an obvious one? How can I harness some background cycles or background idleness to prepare myself for the future? Yeah. Yeah, page cleaning, right? I write the pages out, I synchronize their content on disk, and now when I suddenly need a huge, chunk of memory because you started Photoshop or something, I have a bunch of clean pages lying around that I can immediately evict, right? So this is another, and these are, again, these are just sort of canonical hits, right? All right, one more, right? Shed load. This is an interesting one, right? Shed load. And actually, in the context, maybe we're going to have a couple of extra lectures this year, which is pretty cool. Maybe one of the ones I'll do is on web server performance, right? So for example, one thing that certain varieties of web servers will do is if you imagine the relationship between the number of requests that they're receiving and the number of requests that they're satisfying, right? At some point, I'm going to use my magical laser thing here, although I hate when people do this, right? At some point, it goes like this, right? As requests come in, they get processed, and the more requests I get, the more requests I process, right? Obviously, this curve can't go up and to the right forever, because what happens? Yeah, I mean, there's some limit, right? At some point, my disk bandwidth starts to be the problem, or my CPU is an issue, or whatever. So once I get up there, what do I want to happen? I want it to look like this, right? So if I'm getting 10 times the number of requests that I can handle, I actually want to be able to keep handling the maximum number of requests that I can receive, right? That way I'm sort of working at a steady pace and working through the backlog. What actually happens on some of these systems? Looks like this. Right? I mean, this is why denial of service attacks work, right? Because with a lot of web servers, if I can flood them with enough traffic, they essentially crow to a stall. They slow to a crawl, and they don't serve anything, right? They're just so inundated with requests that they're constantly, and then their requests time out, and so they never get anywhere. They're like stuck running a little loop. I feel this way sometimes, actually. I'm just like stuck processing my input queue, and nothing actually ever makes any forward progress because there's a lot of stuff that you need to do to serve, a web page from a modern sort of dynamic website, right? So what's a case in the memory management system? This is interesting, where I would need to shed load. Yeah.
When it's thrashing.
Okay, yeah, it's thrashing. So what and what would I do? What would I do to shed load in this case, right? What's my load? Yeah, Natasha.
What does shed load mean? You didn't quite get there in your explanation.
I didn't? So shed is just get rid of, right? Get rid of load, right? If I get overloaded, I need to somehow get myself back into a good place, right? So thrashing is a good example because what happened when I'm thrashing is that all the page activity has actually reduced the performance so dramatically that it would be better to get rid of some of the load than to keep trying to suffer under the load that I'm under. So what can I do? How do I shed load? So again, what's load in this particular case? What's generating the load? Applications, right? Tasks, processes. So how do I shed load? Kill them, right? I'm serious. And actually on Linux has this out-of-memory killer, right? Because when Linux runs out of memory, what else can you do, right? You could reboot, right? But this is like a little bit of a gentler version of that, right? Which is, it's not super gentle, right? But there is this algorithm for figuring out like, which is the unlucky process that I'm going to kill, right? I'm serious. I mean, you can look, there's this whole algorithm in Linux for the out-of-memory killer, right? And I have no idea how it works, right? But the general approach is simple, right? When I run out of memory, I can stop launching new processes, but just start killing the ones that are there, right? And the system looks for processes that have a big footprint because it's going to be an improvement. It avoids certain processes that are important, right? If they're the problem, then you're probably in deeper trouble than it can get you out of. But yeah, I mean, at this point, your back's up against the wall. There's nothing to do, right? There's no good solution here other than to just start killing processes. And again, it doesn't do it at random. It does it based on the output of this completely dark art algorithm. Right?
I think we should kill init.
Yeah, that's not, yeah. Init is, I think, not usually at the top of the list. Unless, yeah, if you want to reboot. So anyway, so these are, and again, go grab this paper, and there's a bunch of other ones in here that are nice, right? These are not, the paper itself is titled Hints for Improving System Performance, right? These are not, and he's very honest about the fact that a lot of these, if you read through the full paper, are self-contradictory, right? They don't all apply in all cases, right? And if you tried to follow them in all cases, you'd find yourself them fighting against each other, right? But the idea is to build up a set of techniques that you can then apply to problems on a per problem basis once you have an understanding of what a particular performance problem needs, all right? So on Friday, we're going to start talking about virtualization, right? The performance part is sort of one of our last topics, and then we'll do some potpourri stuff at the end of the semester. So I will see you guys on Friday.